Good morning, students. In today's session, we will start with a new topic, that is periodic table and periodicity. Students, you all know that before the construction of periodic table, many scientists gave their idea before coming of modern periodic table. Let's recall who are the scientists who came and went, who gave their ideas for the construction of periodic table. First, Dobrenier. He was the first scientist in the 18th century who gave the periodic table, which was in the law of triads, that is Dobrenier. He was nothing but, he gave a famous law, that is law of triads. In law of triads, what Dobrenier did means, he arranged the elements, that is 3 elements, in the increasing order of their atomic weights. He arranged the 3 elements, that is if I take A, B, C, the element A, B, C. He told that the mean of element A plus C divide mean of element A and C gives the atomic weight of B. That is if I take an example of lithium, then sodium and potassium. He said that the sodium, atomic weight of sodium was the mean of atomic weight of lithium and potassium. That was the law of triads. He took 3 elements which were having the similar properties according to Dobrenier's law of triads. His law was discarded because when the arrangement was seen in the law of triads in the 3 elements, there was certain not matching values were present in it. That is, the mean was not exactly the atomic weight of middle element. So his law was discarded. Before there were only 31 elements in 18th century. After 1863, then came a scientist by name Newland. He gave a law, he gave a law, that is a famous law, law of octaves. This is the famous law given by the Newland in 18th century, where he placed the elements in the periodic table in the increasing order of their atomic mass or weight. He placed the elements in the increasing order of atomic weight. That is law of triads. What is this? Sorry, law of octaves. What is this octave? The meaning of octave is tune. Means Newland, he was having a affection towards music. So what he did, he placed the elements in the order of music. Like you all know, there is a music that is sa, re, ga, ma, pa, da, ni. That is 7. That is sa, re, ga, ma, pa, da, ni. All this is first, second, third, fourth, fifth, sixth and seventh. Here he told that the 8th element that comes has the same property of the first element. That is nothing but law of octaves. He mixed the chemistry with the music. That is, he said that sa, re, ga, ma, pa, da, ni. After ni, again the 8th element is the repetition of the first element. It shows the properties of the first element. Like this, he arranged the elements in the periodic table. Only in this periodic table, in Newland's periodic table, there were only 31 elements up to calcium, which were light elements. But this law was not applicable for the higher elements. After the discovery of higher elements, this law was discarded. Then came Henry Moseley, that is Dmitri Mendeleev. We know that His law, his periodic law is famous. He gave a periodic law, that is Mendeleev's periodic law. According to him, he said that he arranged the elements in the increasing order of their atomic weights. He arranged the elements in the increasing order of the atomic weights. He took the idea of Newland, that is, he arranged elements in the increasing order of their elements, but he did not accept octaves. He said it is not octaves, that is, the repetition doesn't take place at 8th element only. He told about the periodicity. Even the Newland, he gave the idea of periodicity. He said that there is a repetition of elements at certain fixed or at certain position, that is periodicity. In this, Dmitri Mendeleev, what he said, it is not octaves, but after the discovery of noble gases, what happened? This law of octaves was cancelled, because here there were no discovery of noble gases. After the discovery of noble gases, this law was discarded. He said that here it may be a repetition, periodic repetition of the elements takes place at certain trends, that is fixed trends. It may be at certain regular intervals or fixed intervals. The repetition of elements takes place in the fixed intervals, that is nothing but periodicity. He explained about the periodicity. The repetition takes place at the certain regular fixed intervals. This was the law given by Dmitri Mendeleev. He placed the periodic table which had the 7 horizontal rows, 7 horizontal rows, which is called as a period, and 8 vertical columns called as groups. In his periodic table, in Dmitri Mendeleev's periodic table, there were 7 horizontal rows called as periods and 8 vertical columns called as groups. In these periods, there were subgroups. In groups, there were subgroups also. Then, in his modern periodic table, what was the advantage means, this Mendeleev, what he did means, in his periodic table, he left some places in between the elements. If I see here, scandium, or if I take any elements like strontium or aluminium, like that. If I take aluminium, then silicon. If I take aluminium and silicon in the periodic table. He left the gap here in between these. There was a prediction for him, because the atomic weight of this aluminium and this element were having more difference in their atomic weight. So he had a prediction. So he left places in between, and he named it as Eka aluminium and Eka silicon. And he said that they had similar properties of aluminium and silicon. Therefore, he named it as Eka aluminium and Eka silicon. Then a modern periodic table came into existence by Henry Moseley in 1813. In 1813, Henry Moseley gave a modern periodic table, or the long form of periodic table. 1813, a modern periodic law was given by Henry Moseley. He gave a modern periodic table, or a long form of periodic table, which had, this is the modern periodic table which was constructed by Henry Moseley in 1913. His modern periodic table was given in 1913. That is nothing but a modern periodic table or a long form of periodic table. Here Henry, what he did, he took there was a discovery of nucleus. That is, the nucleus consists of what? Electrons, protons. Electrons and protons were present in the nucleus. In nucleus there were electrons and protons. And also a new term called as atomic number came into exist. That is, we use the symbol Z for atomic number. Atomic number means what? Number of protons that are present in an atom, or number of electrons. Number of protons or number of electrons is nothing but a atomic number. Henry Moseley, what he did, he told that, or he arranged elements in the periodic table in the increasing order of their atomic number. Increasing order of their atomic number. Henry Moseley, what he did, before they were placing the elements in the increasing order of their atomic weights or atomic mass. Here Henry Moseley, what he did, he placed the elements in the increasing order of their atomic number. And after placing the elements in the increasing order of their atomic number, they came to know about the X-ray diffractions, spectrum of X-rays, as well as frequency. The term frequency and X-rays came into existence. And then what this Henry Moseley did means, he plotted a graph where atomic weight number was taken here and frequency was taken along this axis. X and Y axis along this, atomic number and frequency was taken. What he did, he took the elements like hydrogen, helium, lithium, beryllium, boron, and he incidented on the X-rays. When these elements were incident on the X-rays, you all know that it is in the form of electromagnetic rays. That is, electromagnetic rays are emitted through X-rays. When these elements were incident on X-rays, what happened? There was a gradual increase in the graph. That is, if the atomic weight number was hydrogens is here, then helium came here, then came beryllium, then boron. Like this, there was the increase in the atomic number. They emitted certain frequencies and it was plotted in the graph. The graph was straight line. The graph was straight line. So he told that, and he placed the elements in the increasing order of their atomic number. That is the modern periodic law that was given by Henry Moseley. We know that the atomic size also and the nucleus size also, no, in the periodic table. So the size of the nucleus is very small compared to the atom size in the element. Next is, we came to know about the periodic table, how the periodic table came into existence. And you all came to know about the periodicity. What is periodicity? It is nothing but the repetition of physical and chemical properties of an element. Repetition of the physical and chemical properties of the element at certain fixed intervals, or certain fixed intervals is known as periodicity. That is periodicity. Periodicity is nothing but repetition of physical and chemical properties of the elements at fixed intervals is called as periodicity. Why this periodicity takes place? Due to repeated or the reoccurrence of similar outer electronic configuration of some elements. The periodicity takes place. Henry Moseley divided the periodic table into 7 horizontal rows called as periods and 18 vertical columns called as groups. He divided a periodic table into 7 horizontal rows called as periods and 18 vertical columns called as groups. Again, this periodic table was further classified into 4 different, that is S, P, D and F block. Different 4 blocks were, it was divided into different 4 blocks. It was divided into 4 blocks. That is S block, S, P, D and F block. There were 4 different blocks in the periodic table, as you all are seeing the 4 different blocks in the periodic table. Let us come what are the properties of these block elements. Coming for the first one, that is S block element. S block elements. Here S block elements means what? These are the elements where the valence electrons means what? Outermost electron. They go into S subshell or S orbital is called as S block elements. The valence electrons enters into S orbit is nothing but S block elements. These are called as S block elements and they have the general electronic configuration. Their general electronic configuration is NS2. This is the general electronic configuration of S block elements and in this S block elements there are 2 groups, that is group 1 and group 2. Here you all can see the modern periodic table here where there are 2 groups here. This is group 1 and group 2. This is group 1, group 2 here. That is, if I take electronic configuration of group 1 is NS1, this is NS2. Here if I take an example of lithium, that is atomic number is 3. I can represent it as 1s2 and 2s1. Electron is filled in lithium. So here the N is from 2, 3, 4, 5, 6, 7. Not equal to 1 because hydrogen is separately placed here. Then if I take the example of beryllium, that is atomic number is 4. Here 1s, 2s. All the 4 electrons are filled in this, 1s 2 electrons and 2s 2 electrons. Here N value is between 2, 3, 4, 5, 6 and 7. Not equal to 1 because helium is placed in 18th group. Okay, let's come for the elements that are present in group 1 and group 2. You all can see that the elements that come from N is equal to 2, that is lithium, then comes sodium, then comes potassium, then rubidium and cesium and francium. That is N is equal to 3, 4, 5, 6 and 7. These are all group 1 elements and these are called as what? Alkali metals. These are called as alkali metals. And coming for group 2, here you all can see in the periodic table group 1 elements lithium, sodium, potassium, rubidium, cesium and francium. In group 2, barium, magnesium, calcium, strontium and barium and radium. That is group 2 from barium to radium. All the 7 elements are present in this period, in this group 2 from barium to radium. And these are called as alkali earth metals. These are called as alkali earth metals. These are called as alkali metals, group 1, and group 2 are called as alkali earth metals. Why we call it as an alkali metal? From first only you all know that alkali means what? It has a basic character. Means they are basic in nature. Alkali metals are basic in nature. When they react with hydroxide, they form basic nature. Therefore, they are alkali metals. They are basic in nature. And they are obtained in the form of salts. That is sodium, lithium, potassium. All these are in the form of salts. They are in the form of salts. Okay, you obtained it in water in the oceans. Coming for alkali earth metals, these alkali earth metals, these are found in earth crust. Therefore, they are called as what? Alkali earth metals. Coming for the properties. Properties of this S block elements. Here, these group 1 and group 2 elements, they have low ionization enthalpy. They are having low ionization enthalpy. Their ionization enthalpy is what? Low. They are having low ionization enthalpy. Ionization enthalpy means what? The amount of energy that is required by an atom to remove an electron is nothing but ionization enthalpy or ionization energy. Here, ability to lose electron is nothing but ionization enthalpy. You all can see here how many valence electron it can lose. In lithium, there is only one valence electron. In beryllium, there is 2 valence electron. According to octave, you require to complete octave, it requires 7 electrons. Here it requires 6 electrons. It is highly impossible to get a 7 or 6 electrons, but it is easy to lose the 1 or 2 electrons from it. Therefore, what these elements do, these alkali and alkali earth metals, they have the ability to lose the electrons. Here, group 1, they lose 1 electron. Group 2, they lose 2 electrons. As you all know that they have the low ionization enthalpy and also they have the ability to lose the electrons. Therefore, what happens? Their metallic character increases when it goes from top to bottom in the periodic table. Metallic character increases. There is increase in the metallic character because why? They donate the electrons. They have the ability to donate the electrons, and therefore they are, most are electropositive. Electropositive elements. They are most of them are electropositive in nature. This is about the S block elements. It's clear now. The S block elements is what? They are nothing but the valence electrons enters into S subshell, and they have the general electronic configuration NS2. It consists of 2 groups, that is group 1 and group 2, NS1 and NS2. Here coming for group 1, they are called as alkali metals. Group 2 is called as alkali earth metals. Alkali means it is basic in nature. Coming for the properties, both has the same properties, that is they are having a low ionization enthalpy. Their enthalpy is very low, means they have the ability to lose a electron. Here group 1 loses 1 electron, group 2 loses 2 electrons. Since they have the lower ionization enthalpies, therefore their metallic character increases as we move from top to bottom. And also most of them are electropositive metals. They are all electropositive metals. Next is p block elements. Here s block elements are to the left and p block elements are to the right side of the periodic table. These are present to the right side of the periodic table. P block elements are present to the right side of the P block periodic table. These P block elements means what? The valence electrons enters into P subshell. Valence electron enters to P subshell or P orbit. Is called as P block elements. And these P block elements, you all can see in the periodic table, it comes from 13th to 18th group in the periodic table. From group 13 to group 18. Group 13 to group 18. All these are P block elements. In this P block elements, they have the general electronic configuration. General electronic configuration is NS2, NP 1 to 6. This is the general electronic configuration of P block elements. Coming for group 13 elements, that is from boron. Boron, that is N is equal to 2. Boron to nihonium, that is N is equal to 7. It is in 7th period, that is nihonium. These are also called as boron family elements. They are called as boron family elements. Group 13 elements are called as boron family elements. Coming for group 14, that is from carbon. From carbon to flavorium. These are called as carbon family elements. And they have the general electronic configuration for this boron family, NS2, NP1. For this NS2, NP2. Group 15, that is from nitrogen to moscovium. Nitrogen to moscovium. They are called as nitrogen family. These elements are called as nitrogen family elements. Also they are called as nicogens. They are also called as nicogens. Then coming for group 16, that is from oxygen to livormium. Oxygen to livormium. They are called as oxygen family elements. And they have the general electronic configuration. For this it is NS2, NP3. For this NS2, NP4. Next is group 17. That is from fluorine to tennessine. Fluorine to tennessine. This is group 17. They are also called as halogens. Coming for group 18. Group 18 elements. Here for this the general electronic configuration is NS2, NP5. For this NS2, NP6. And group 18 elements are also called as inert gases. Inert gases or noble gases, because they won't react with any. That is from helium. You all can see from helium to augmentation. Here the helium is in n is equal to 1, first period. Then after helium it comes neon. It is in second, that is fluorine, oxygen, all this comes in the order of second period. Helium is in first period, is equal to 1. These are called as inert gases. Here when I see this group 13 and 14 elements, when it moves from top to bottom in the periodic table, their metallic character increases. All this group 13 and 14 elements, both their metallic character increases. Coming for group 15, that is nitrogen family, these are also called as what? Nicogens. Why they are called as nicogens? Because these elements are poisonous, poisonous in nature. Therefore, they are called as nicogens. And then coming for group 16, oxygen family elements. Here these oxygen family elements are also called as ore forming elements. They are also ore forming. They are also called as ore forming. Oxygen family elements are ore forming, and these halogens, these are salt forming elements. These are nothing but salt forming elements. And group 18 elements, as I said, they are inert gases or noble gases. They are group 18 elements. Coming for the properties. Come here, as we move from group 16 to 17, what happens? They have the tendency to accept the electrons. You see the oxygen, fluorine, all this, they have the tendency to accept the electrons. Group 16 and 17 elements. Group 16 and 17 elements. You all can see they have the tendency to accept electrons. Therefore, here what happens when you move from left to right? When you move from left to right in the periodic table, what happens? Non-metallic character increases. There is increase in non-metallic character. When you move from left to right in the periodic table, you all can see that oxygen, fluorine, they have the tendency to accept the electrons. Therefore, they are non-metallic in nature. But S block elements have the metallic character because they have the tendency to lose the electrons. And also, here you all can see the group 18 elements. They are inert. They won't react with any other elements. So, they are called as inert elements. These group P block elements are, most of them are electronegative in nature. Electronegative in nature. They are electronegative in nature. And also, they are electronegative in nature. They have positive as well as negative oxidation state. Positive and negative oxidation state. This is about the properties of P block elements. Next is D block elements. Here, these D block elements, they are also called as transitional elements. They are called as transitional elements. What is the meaning of transitional? Transitional means it acts like a bridge. They are like nothing but bridge forming elements. You all can see in the periodic table, S block is this side to the left and P block is towards the right of the periodic table. And in the middle you all can see the elements from group 3 to 12. These elements are called as D block elements. They are placed in between S and P block elements. Therefore, they are called as D block elements. They are placed between S and P block. Here, if this is the S block elements, here you all can see S block elements and P block elements here. The D block elements are placed in between S and P block elements. Therefore, they are called as what? Transitional elements. Here, in this transitional elements, you all can see 4 series. That is 3D series, 4D series, 5D series and 6D series. Coming for n is equal to 4, that is 3D series. In 3D series, here the elements are from scandium to zinc. They are from scandium to zinc. That is 3D series. The outermost electronic configuration is 4s2, 3d, 1 to 10. This is the outermost electronic configuration of 3D series. Coming for n is equal to 5, that is 4D series. Here, yttrium to cadmium. They have the general electronic configuration, outermost shell, that is 5s2, 3d, 1 to 10. Then n is equal to 5, that is 5d series. That is from what? Lanthanum, that is 57 is lanthanum to mercury. Lanthanum to mercury. They have the outer electronic configuration 5s2, sorry, here n is equal to 6, 6s2, 3d, 1 to 10. Then n is equal to 7, that is 6d series. Here in 6d series you all can see from 89, atomic number 89 is actinium. Actinium to copernicium. Actinium to copernicium. These are having the general electronic configuration, that is 7s2, 3d, 1 to 10 here. Here you all can see in this D block elements, this is the ultimate shell and this is the penultimate shell. Here, if I take any atom, this is the first floor of the atom, second floor and third floor, and this is the fourth floor of the atom. According to Aufbau's principle, how we fill the electron? 1s, then 2s, then 2p, then 3s, then 3p, then in 4s, then 3d. The filling first takes place in where? 4s subshell. Then 3d subshell fills here. Here, if I take 4s, that is the outermost ultimate electron is in 4s here, S subshell, that is 4s, and 3p, 3s, 3p, 3d. You all can see here. After filling of this S subshell only, 3D subshell fills. This is the ultimate shell and this is the penultimate shell. Therefore, before we were telling what is S subshell, S block elements means the valence electrons enters into S subshell means it is the S block elements, and P also what? If the valence electrons enters into the P subshell means P block elements, but not in case of D block, because here what happens for the explanation of D block is that here the filling of n minus 1 here into D subshell is not completely filled. It is not completely filled or partially filled. It is called as D block elements, where the elements in the D block elements n minus 1 into D subshell is not completely filled or they are partially filled. Therefore, they have the general electronic configuration Ns2, then Np 1 to 6, then n minus 1 into D 1 to This is the general electronic configuration of d block elements. Here, coming for the, you all have seen 3D series, 4D series, 5D series and 6D series in the d block elements. Coming for its properties, what are its properties? Here, coming for the properties, most of them are, all are metals, okay. In d block, all are metals, all are metal. And they have certain properties like they are colored compounds. They are colored forming compounds. They are colored compounds. And they have the magnetic property. Most of them have the magnetic property, and that property is, most of them are paramagnetic in nature. They are paramagnetic in nature. Most of them are paramagnetic in nature because they have unpaired electrons, and they are good catalysts. They are good catalysts. Also, they have variable oxidation state. Variable oxidation state. This is the some of the properties of d block elements. That is, all are metals and they are colored forming compounds, and they are having a magnetic property. The elements has magnetic property. Most of them have the paramagnetic in nature because the presence of unpaired electrons, and they are good catalysts, and also they have the variable oxidation states. Next is F block element. Here, F block elements, these are the elements which are placed below the periodic table. You all can see that in the periodic table there are two blocks that are kept below the periodic table. That is nothing but F block elements. They are also called as inner transitional elements. Here in F block, if I take n is equal to 6, n is equal to 7. That is cesium, barium and lanthanum. Cesium, barium and lanthanum. And n is equal to 7, that is francium, radium and actinium. Francium, radium and actinium. In this, they have the electronic configuration, that is 6s2 and 5d1 in the outermost subshell. And here for this actinium, for this lanthanum it is 6s2, 5d1. For actinium 7s2, then 6d1. This is the outermost electrons where the electrons are present in d subshell in this F block elements. This lanthanum, if I take the lanthanum, you all know that the filling of electrons takes place where here after 6s it comes 4f, then comes 5d. In n is equal to 6. In n is equal to 7, the filling should be, that is 7s, 5f and 6d. You all know, according to Aufbau's principle, the filling should be like this. Here in this, what happens in lanthanum and actinium, in any atom, in the center of the, this is the center of the nucleus, you all know that in an atom it is the center of the nucleus, and these are the different orbits. There are different orbits in the atom. If I take d and f subshells, in this case, in this F block, okay, in this case, here between the F and D there is no such difference. You can't make out the difference between the F and D block in this orbit, that is F and D. Therefore, what happens, the electrons, the outermost electrons take the position of D in this, and if it is having more than one electron, then only F subshells comes to filling, okay. you all can see that after this lanthanum, there were certain elements that is from cerium to lutetium, from cerium to lutetium, and from thorium to lawrencium. These are nothing but F block elements. Why these are kept in F block and this lanthanum and actinium are kept in D block? Let's see now. As I said, there is not much difference between the F and D subshell in this orbit. So, if there is only one electron, then only D subshell fills here. Then if there is more than one electrons, what happens? F subshell fills first, then filling takes place in D subshell. Coming for lutetium and lawrencium. This lutetium has the electronic configuration that is 4f1, 5d1. Then lawrencium, that is 5f2, 6d0. This is the outermost shells, electrons that are present in the outermost shell of these elements, that is lutetium and lawrencium. Here you all can see in cerium, sorry, not in lutetium and lawrencium, that is in cerium and thorium. This electronic configuration for cerium and thorium, that is 4f1, 5d1, that is 5f2, 6d0. For cerium it is 6s2, 4f1, 5d1, then this is 7s2, 5f2, 6d0 for thorium. You all can see that there is a general increase in the filling of F subshells taking place after cerium. After cerium is what? Praseodymium, then comes neodymium. Like this, the filling of electrons takes place up to lutetium in F subshells. From F is 1 to F is 14, the filling takes place here. Here from thorium, that is F is 2 to F is 14. The filling of electrons takes place in F subshell. Here in this elements there is incomplete filling of F subshells. Therefore, they belong to F block elements. In these elements there is incomplete D subshell, that is in lanthanum and actinium there is incomplete D subshells. Therefore, they belong to D group elements, and these belongs to F block elements because they are having incomplete F subshells. And here you all can see after lanthanum the element cerium to lutetium, they are called as lanthanoids. They are also called as lanthanoids. They are called as lanthanoids because why? They come after lanthanum. That is from thorium to lawrencium. They are called as actinoids. Why they are called as actinoids? Because they come after actinium. Coming for the properties, even these all are metals. These F block elements are metals, and most are radioactive in nature. They are radioactive in nature. The elements are having a radioactive nature. And the elements that comes after uranium, the elements which comes after uranium are called as post-uranium elements or trans-uranium elements. They are also called as trans-uranium elements because why? They are radioactive in nature. They are radioactive in nature. Therefore, they are called as post-uranium or trans-uranium elements. And they have a small half-life period. Their half-life period is small. Half-life. Half-life is very short. Okay, they have short half-life. And you can get them, they are found in nanograms. They are obtained in nanograms. These radioactive elements are obtained in nanograms. These are some of the properties of F block elements. In this session, you all came to know about the classification of elements, that is the periodic table according to Mosley. He divided the periodic table into 4 groups, that is S block, P block, D block and F block elements. In complete, I have explained you all about the properties of S block, P block as well as D and F block elements. Here, the general electronic configuration of this F block element is NS2, N minus 1 D, 0 to 1, N minus 2 into F, 1 to 14. This is the general electronic configuration for F block elements. Okay, in detail I have explained you all about the. In the next class, we will come to know about the periodic trends in the periodic table. Thank you, students.